So I'm just going to take a couple of minutes to try and set out what we're going to try and do. And then Georg is going to take over and take us through the main content and ask us, get us thinking about some questions and ask us some questions, I think. So just to set the scene, the idea of the Subsurface Rendezvous was to have a sort of regular online event that is not a webinar. So the idea wasn't supposed to be this one-way just broadcasting of information out. And it was sort of to try and experiment with seeing that we're all online anyway, can we get the online format to work better for us and actually have something interactive where we can have a proper discussion and also maybe capture the output of that discussion and actually do something rather than just listen to a one-way webinar. So we came up with this format that we're still figuring out, but the idea is to have a live session, which we're in now, which I guess can last anywhere between 60 and 90 minutes. And for that to be part talk and part discussion, which Georg's going to lead us through. And it's live streamed to YouTube. There's also a Slack channel available so that we don't have to be constrained by these 60 minutes and we don't have to also think of all the questions right now. We can come back later and contribute and continue the discussion if we like. That's one of the things that always got me about real workshops is a lot of the time that there's never enough time for questions. And me, I'm often one that I'll think of a question 2 hours later or the next day and not immediately after the talk. So the idea was, because we've got an online forum, can we just stretch out and open up the time to let more people contribute and to let that contribution happen at its own pace? And we also put it on YouTube because then not everybody can turn up to the live event. Some people are in Australia, some people are on different time zones or just can't make it. And this is a way that, you know, maybe they can also watch the live stream and then come in and actually contribute something in Slack later if they're able to do that. So that was the idea of the session, and let's see how far we get and where it all takes us. So today things are about the talks about Geohub. So for reproducible geomodels, and Georg is going to take us through some slides in a minute and a demo, I think, of his system and what he's been building. And what I'd like us to do is to try and capture some notes and any questions. Obviously, there's a lot of people in the chat here. And so rather than just saving up your questions and shouting them out, maybe we could use this Google Doc. Everybody should have the link, but if not, it's quite an easy one to type in, bit.ly/geohub RDV. And that's just roughly divided into 2 sections for questions and notes, but we can change that however we want. So feel free to type in there, make notes for yourself and for the group, and note down any questions, and we'll definitely work through all those questions. And for anybody who's not yet on Slack, on the Slung Slack, there's a channel, SSRDV Geohub. And after the event, we'll copy all the information in there and keep the channel going, keep the discussion going. I had also thought that there might be quite a lot of people here. There's not like the 55 who signed up to Eventbrite, which might have been a bit crazy to have a discussion around anyway. But I think the idea is, obviously this is an open Zoom meeting. Anybody can unmute at any point, and we'll just have to figure out and be aware of talking over each other and stuff and things like that. If there is a discussion going on and you'd like to sort of raise your hand, I'll be watching the chat channel, and you can just drop a message in the chat, and I'll make sure I'll help you get into the discussion. Okay, so that was it in terms of introduction, what we're trying to do. So I'll pass over to Georg now, if you'd like to share your screen.
So then welcome also from my side. my talk is about Geohub, which is basically my PhD topic. It's a database system to manage reproducible geomodels. And the motivation here is digital geoscientific models are used by more and more scientists, and those models are getting larger and become more complex. And this means it's getting harder to understand how a model was built. But in my opinion, it's required to understand how a model was built to comprehend and reproduce the research results of other research groups. So to give a short anecdotal example here, at our university, I've working together with a group of geophysics, and they shared a data set and some scripts for processing and interpretation with me, and asked me to have a look at the results. So they told me we store our code in a GitLab instance. It's there. We store our data on this shared file system there, and they also had a continuous integration system for their GitLab instance based on Docker. So everyone thought it should be simple. Georg just need to start up the Docker image, copy the data into the image, and run those scripts. So that should be easy, right? So reality was quite different. I've tried to start the Docker image. That didn't work because somehow they managed to mount the MATLAB installation from the host system into the image. So I thought, just install MATLAB and then I should be able to run those scripts. No, that didn't work either, because their MATLAB code required some more dependencies that need to be installed. At that point, I get their Docker file and looked through the Docker file and noticed that there are quite a few native dependencies, like some mathematical Fortran code. So each of them required I call it special compiler setup. You need to figure out how to use the build system for those libraries, and you need to figure out where to put the compiled libraries. So yeah, it's quite a complex process. So I got everything to work after some days of searching for issues, but I think I've started at a quite good position there, because I've had access to the code, to the data, and even to a Docker file describing which dependencies were there. I think the reality somewhere else is quite different. So in my opinion, that was even the easy version of the problem. So looking back at those specific problems, I've identified a few problems there. First of all, reproducing the construction of a model requires you not only to reproduce the construction itself, but also to reproduce the environment used to construct the model. This includes all applications that are used to construct the model, in the best case at the same version as used for the original construction. Then each of those applications can have a rather large list of dependencies. You need all of them. And each of those applications can require some special configuration of the environment or operating system. Then obviously to reproduce the result of a construction process, you need to have access to the initial data sets that are used for the construction. And then you need to know which construction step needs to be done in which order. So basically when to run which script. And there's probably a lot more I've missed here. That's the point for the discussion later on. So some of you now may want to tell me, yeah, there are existing solutions for this. So for example, there are solutions to store geoscientific data sets, for example, PostGIS, or just store them in a file system. There are solutions to manage your code like Git, and there are solutions to describe an application environment like Docker. Yeah, each of those works quite well on its own, but there is currently no way to verify that everything would work together later on for another researcher to reproduce your examples, your models. So the next few slides I want to use to introduce a few terms and definitions. I think the question about what's a geomodel or geoscientific model already turned up. For me, it's just abstract geoscientific construct used to approximate the reality. And it's usually based on measurement data. Examples here are subsurface models, but also cross-sections or seismograms are geoscientific models for me. Then I've used the term dataset quite a lot. Dataset for me is a set of measurements or interpretations or nodes that are grouped together somehow as logical unit. They are used to construct the geoscientific model. Examples here are data from geophysical measurements or digitized cross-sections or remote sensing images and so on. For Geohub, I classify datasets in input datasets, which are datasets that are used to initially start the construction process. Those are assumed to be provided by some external source or based on measurements. Then there are intermediate datasets. Those datasets are basically generated as part of the construction process. Then there is the term of a construction step. This is just some piece of work that is required to transform one dataset into another as part of the construction process. And also there's the term project, which just summarizes a complete construction process, including all required input data, the list of construction steps, and the final geoscientific model. So as I'm a PhD student, I want to build something new, and the idea is to build a new system to manage all those data. And I think it's a good idea to store everything in one place. This includes all data sets and construction steps that are required to create the final geoscientific model. Because if you not have one or the other, you cannot reproduce the construction process later on. Then we want to be able to repeat the construction of the model at any later point in time, and that should hopefully accomplish the same model. This means each construction step should be executable by a computer. And as always with geoscientific data, keeping track of metadata is important because if you don't know where your geoscientific model is located, the model itself is probably not that useful. The core idea of the new system is something I've called construction hypergraphs. Basically, a construction process of a geoscientific model can be described as finite directed acyclic hypergraph, where each node in this hypergraph corresponds to a dataset used to construct the model. Each hyperedge in this construction hypergraph corresponds to a construction step transforming one group of datasets into a result dataset. Basically, each of those construction hypergraphs represent one project. As this description is quite abstract, I've put together here a small example hypergraph. It's just an abstract example, so don't put too much meaning in each operation and dataset here. Basically, in this example, the dark green nodes are datasets, while the light green edges, light green squares are operations. The direction of the arrows indicates that data set is used by some operation to produce another data set. It results in the final subsurface model here. Yes. So how does a construction hypergraph help us to provide an reproducible way to manage geoscientific models? Given such a construction hypergraph, we can easily reproduce the construction at any later point in time, because we just need to re-execute the whole construction hypergraph again. To make this process reproducible, we place a few assumptions on each construction step. Basically, we are saying, okay, if we are executing a construction step twice at different points in time, this should lead to the same results. If it doesn't, the construction step itself is not reproducible, and therefore the construction process of the whole model is not reproducible. Obviously, this assumes that the input data do not change between two such repetitions, because if you change the input data, it's expected that it can be expected that the output data are changed later on. The next few slides I want to use and talk a bit about the implementation of this idea. Basically, I've chosen to implement this as a microservice architecture. There's a client web app which provides some kind of user interface. There is a main service which manages the actual data sets in different locations. And there are operation-specific executors which supports executing construction steps using existing tools. Here's an abstract overview of the application. Basically, the user interacts with the client web app. That's just a HTML single-page application. The web app communicates with the main service, where the main service is responsible for managing all data. The actual data sets are stored as binary blobs on the file system, while metadata and system internal informations like which users are allowed and so on are stored in a relational database system. The main service also schedules operations which are executed as part of the construction process. Those scheduled operations are passed to so-called task runners, which run those operations in a user provided environment, user-defined environment. There can be more than one task runner just to parallelize and speed up the execution of independent construction steps. I think the most interesting part of the implementation is the implementation of those task runners and therefore the construction steps. Because of that, I will talk about that a bit more in the next few slides. First of all, we placed a few assumptions on construction steps to make this even possible. The first assumption is, I've already introduced the first assumption. It's required to execute a construction step by a computer. This means there cannot be a human interaction. This is required because we want to repeat the construction step at any later point in time. For reproducibility, a construction step needs to be deterministic, because otherwise you pass in some value and every time you're calling some construction step, another value comes back, and how would you reproduce that? And for now, an assumption that is based on the implementation is that construction step needs to be described as some sort of script in a user-provided Linux environment. Again, a discussion point for later. How well would this work for you, for your use case in practice? So how is this implemented? Basically, it uses Docker internally. The user provides a Docker image, which allows them to install any software that is required to execute their specific construction step. The operation then is defined as script. This script is executed in an instance of those Docker image. Metadata and input data sets are written at some defined location into this Docker container. After all operations are executed, the output data are received from the Docker container. Yeah. On this slide, I have an exemplary step definition. It starts with saying which image should be used to execute this step. After that, it just lists a number of commands which should be executed as part of this construction step. In this example, it's just one command which runs some fancy calculation. It's just an example. And then it defines which files are expected as output. If something, if any of this fails, there's an error returned to the user. Yeah, so I've talked a bit about I've implementing stuff. So what's the current status of the project? Basically, I have an existing prototype that implements at least some parts of the concept. I've implemented already several example construction workflows using that prototype. And as next step, I will just show a short demo. Hopefully that's visible for everyone. Okay. I've already created some example project that we can use for our modeling now. Yeah, I should say it's just a prototype and I'm not a web developer, so it probably doesn't look that nice and usable in most cases. it's just showing that the concept is working, basically. Yeah. Let's define some input data set. Let's call this input, and I have some geophysical measurement data here. It's a seismic measurement, basically, as far as the geophysicists told me, some sort of tomography. Those are the travel time peaks. I've just attached them to the input node. Then I will create an output. And we need to define our operation, which connects input and output. So I've already typed the step definition in an editor, so we will look at that in a second. I've just copy and paste this here because typing that all in here is quite not that great. So if you now look at the definition of our graph, it's quite simple. It has one input, one output, and a construction step in between. It defines, it uses an existing image I've put somewhere, and it then defines one operation, which basically starts an existing MATLAB script in the container, and then it expects a number of images to be returned. Also, it says currently the operation is in an unknown state because we haven't saved the construction hypergraph yet, so the server could not do anything. So I've just submitted that to the main service, and now the color of the operation changed. And if we now look at it, it says it's scheduled. And as this is a prototype, I haven't implemented any sort of live reloading yet, so I just need to reload the project. The color changed again. Now it's started on some executor in the background, and we can have a look at the operation log, which is basically the output of our operation. It just says it started MATLAB and is doing something. As I'm seeing the executor in the background, I know we need to wait a few more seconds, as this is a geophysical simulation. It takes some time. Hey, it's telling me I shouldn't use that much CPU. Hey. It's calculating. It continues to calculate stuff. The log is getting longer, so that's fine. And hopefully it should be ready soon. Yeah. That's a good example. Waiting for the simulation to finish. I should probably choose something simpler the next time. It looked like the simulation has finished yet. So the operation state now says successful. And if you look at the output, we get a number of images returned. Basically, it's a tomography of some rock formation in a ore mine here in Freiberg, and yeah, so this means you get back hey, you get back velocity distribution for sometimes. But as I'm not a geophysics expert, I cannot tell you much more about this. It's just an example for me to showcase the application. So back to our slides. Yeah. I think there are a few possible future extensions for the for Geohub. For example, it would be nice if the client web app actually visualizes the data sets and not only shows you a download link for everything that is not an image. So yeah. Also, those operations, it would be nice if they can be shared between different construction steps. So the basic idea here is you define once how to do inversion for some geophysical problem, and you can reuse that definition in multiple projects. Another nice idea would be to allowing to parameterize construction steps as each construction, as the construction should be repeatable. This would allow users to build multiple variants of the same project by just changing one parameter slightly, which allows to just see the influence of this parameter on the final model. And also, I've talked a lot about reproducibility. The current implementation just executes each construction step once. Obviously, it needs to execute each construction step at least twice and compare the output to see if the process is reproducible or not. So to give a short summary, basically Geohub should enable the storage of geoscientific models and their construction process. For this, it provides a theoretical foundation for building geoscientific models, and there's a prototype. Yeah, basically the idea is to turn geoscientific models into reproducible geoscientific models. Then, till now, thanks for your attention, and I think that's the point. That's the point for time for discussion.
Great, thanks, George. Oh, clappy hands. Do you want to stop sharing your screen, or do you want to leave it up, or if you?
Depends a bit on the questions.
Yeah.
If there are questions to specific parts of the presentation or the prototype, it may be useful to have the screen share. If not, then
yeah, I think leave it up then. There's a bunch of questions and discussion in the chat. Sorry, in the Google Doc. And I guess where do we want to start? I think there's a bunch. There's some questions around back to sort of defining what geomodeling is and defining what we are trying to do with the system, and they maybe line up with some of your early questions, Georg, on how to. What problems are you trying to solve? Do you want to skip back to that slide, maybe? Oh. I can't hear you anymore.
Oh, sorry.
Oh, yeah, it's okay. Cool.
I've chosen to define the term geoscientific model quite broad because I've noticed while working on this is not only useful for subsurface modeling, but also for geophysical models and probably a lot more models that have a geoscientific application. So
Cool. Does anyone want to ask a question? Or basically, because for the geomodeling side, what was jumping in my head is how specific is the system for particularly geomodeling? And that maybe overlaps with some of the questions about what are we defining as a geomodel? What type of geomodel are we trying to build? You had two-way time picks in your example, but you can bring in well log data?
probably.
Or
that's the point where I should maybe add that I'm more a computer science guy than
I think somebody raised their hand.
computer science researcher, so I've sometimes looked from the outside at those problems, and yeah.
Cool. William, did you put your hand up?
Yeah.
Okay, cool.
I think just to say, I think like a good point Georg has about, this could be more than the standard geomodeling workflow, but I think to easily get it across to people who've sort of been steeped in this in industry. I mean, so I've been a reservoir engineer for years, so like that workflow is drilled in of the everything up to the static, get your stow up, and then start running your dynamics. I think at least if you're able to like very easily communicate, look, this is where this maps onto that, this is where this maps onto the things that you've been doing already, it'll make the sort of communications with people who you would hope to be using this day to day more straightforward. But like saying like this is what you're doing now maps into what I'm describing. What I'm describing can also be bigger.
Oh. Does anyone else want to comment on that? I'm not a geomodeler. I'm a programmer, like a bit like Georg, so I feel really out with depth trying to lead this discussion. So,
hi, can you hear me?
John, you're very low.
I'm going to make it louder. This might be louder, I hope. I have a question, sort of. From my understanding of the presentation, the user, that's the person that creates the model, has to supply a Docker file. And is this correct? And then my question would be, do you think this might put this is a bit out of reach? This is quite a high-end piece of coding that has to be supplied to make the model reusable.
A user needs to supply this Docker image. This does not mean it needs to be the same user which creates the model. That's one of the points I've on the summary slide, on the future extension slide. Basically, the idea is to have someone define the operations, and then the people that actually work on the model can just reuse this operation and say, okay, this is an operation which takes a cross section as picture and leaves as a result the layer boundaries, which then can be used in some meshing or so on.
Who makes the Docker image?
Someone needs to do that.
So maybe you're not thinking the geoscientists on their own would be able to do that. You'd need somebody working. Are you working currently with anybody to use the system?
It's basically this. I've just finished the implementation that far that I can run some workflows there. So it isn't used by anyone yet.
Cool. Are you looking for people to use it? Oh.
Yeah. Sure.
Okay, cool. There's some hands up. Nikita?
Yes, thank you very much, Steve. I apologize, colleagues, for the background noise here. Thank you very much, Georg. I would like to share that we actually in Russia have been using such a system with Dockers. So our users supplying Dockers, and we load it up in a system pretty much like Geohub, but your system is a step forward because you actually connect different pieces together to be able to reproduce the whole workflow. Although I have a question about one of your slides, I saw the definition, it was directed acyclic hypergraphs.
Yeah.
So I guess this is a gap of my knowledge, but I kind of never heard of that combination. Like I've heard about directed acyclic graphs, DAGs, but is there really an implementation of directed acyclic hypergraphs, which to my perspective is basically the graph where edge connects not only two nodes, but more than two nodes. Is there a possibility to make them directed and acyclic? Can you elaborate on that? Thank you.
I will just use this example. Basically, if this were a graph, it won't work because here are two data sets flowing into one operations, resulting into another data sets. These are 3 nodes per edge, which doesn't work for a normal definition of graph. And it needs to be directed because there's a clear direction in which data flows. And basically acyclic is a soft requirement. It just makes the implementation much, much easier. If you don't put the acyclic there, you need to think about, do I have some condition where I will stop recursing through the cyclic graph? So.
Miguel?
Yeah, do you hear me? Yes.
Yeah.
So, first of all, thanks, George, for the talk. Very interesting. It's uncanny how many ideas are very similar to things that we are doing here. So, but my first question, or my main question after listening to your talk, is what your system adds to just being very tidy and careful how you use Git for the input data. So all the data that you use in the first place, the initial data that you mentioned, you do some process that generates other data. Maybe you want to fork it. Maybe you want to just revert to the previous state. So I think that most of the people here, we understand how Git works and the functionality that Git's bringing to the table. I don't know what can you do with your tools that you cannot just do with Git.
I think it adds the environment where you execute the steps. If you basically you can use Git or something like Git to record the data, but then you lose the transformation from one data point to another. You cannot say anymore how you digitize those geological profiles, for example.
But so are you storing the Docker image together with the data in your approach, or how do you save the system or the platform state? So the data state, I think that we understand how to save it, but how to save the system state?
Basically, a Docker image is nothing else than some binary blob that you can store somewhere. So yeah, you
okay,
could do this also with Git, but then again, Git was designed for code, not for large data.
So the idea is always store the Docker image that you have used to process some data together with the data.
In the end, yes. Currently, the Docker image is just stored in some existing repository, but yeah, you could extend it this way.
Okay, I see. Thanks.
So the question, what is actually stored in the database then? The database stores the graph and which Docker images we use in a particular experiment, or?
Yeah. And information about the system itself, which users are allowed to log in, which projects exists, which metadata are attached to existing data sets, and so on.
Okay. So the risk of that is that the database can grow a lot if, for whatever reason, you need many to store many Docker images. I mean, hopefully the Docker image itself doesn't change too often, I imagine, but that has the whole operative system and so.
You won't store the Docker image itself in the relational database because the Docker image is just large there.
Yes, but if you don't save the Docker image, then you are only storing the data again, no?
I guess you can use can you use local Docker hubs and stuff like that? Could you like deploy a Docker hub and then you get
it's quite easy.
Get an image with a hash that you could store.
Okay, I'm just looking for this slide. Basically, I've chosen to store data in two different locations. First of all, there's the relational database where I've stored just, let's call this small data, metadata and system information and so on. This isn't that large. And then there are the geoscientific data and probably in the future, the Docker images. Those are stored on the file system. So basically it boils down how large is your file system, that many data can you store. But in the end, that's always the restriction there.
Yeah, so this is really just to make sure that an experiment is reproducible, no matter how big it is, because you are not supposed to share many of these experiments. Yeah, I see.
Is there any other? I don't know if anybody else has had a look at, because there's various like experiment management systems, like MLflow or Sacred and Comet, and there's probably loads for machine learning. There's loads of, and probably some of those are quite generic. I don't know. Has anybody reached for that type of thing? For, you know, oh, I need an experiment management system. I'm actually going to do my modeling in GemPy. It's the only modeling package, you know. I'm actually going to do my modeling in GemPy, and then I'm going to run these steps afterwards. Has anybody tried to take an off-the-shelf experiment management thing and use that? And I just wonder how it compares to this, where Yoga's, you know, custom built something to try and support.
So on the side of the data, I have seen a couple of libraries, but this idea of trying to link the data to a Docker image to guarantee 100% that you are able to reproduce it no matter what, I didn't see it. that doesn't mean that doesn't exist. I'm not aware. Because usually, if you know the version, or in this case, in your example of GenPy, technically just by knowing the data, you should be able to reproduce it. I agree with Georg that is many times not the case, but
yeah. And that's because of the what's the biggest problem? Is that because of the dependency problem?
Normally it's the dependencies, yes. So you will have to really be able to get the same version of all the dependencies, which to some extent is possible. So technically,
run your own PyPy server and lock that down.
Exactly. So if at each stage of the life of a library is set exactly which is the version of all the other libraries, but then there is always exceptions. Sooner or later, you end up with some compiled code that you didn't take into account and something changed. So I really agree that the only way to guarantee 100% reproducibility, you will have to save the whole virtual machine.
Cool. Great.
I could raise a point.
Sorry. Carry on.
I'm thinking I've never really done subsurface modeling until recently, and the one thing I would say is that this storing the model and the data and using Docker is super cool. And it would work if you're using GenPy, for example, where you have a script written in Python that is running, and you can put that on Docker, and you can have your data, and you could shove it on AWS, and it would all work really nicely. In that, and I created a subsurface model of the eastern suburbs of Paris using GenPy. It was all fun, but my colleagues at work much preferred a better model made with a point-and-click user interface code called SkewerGoCAD. Now, with SkewerGoCAD, yes, after a year of study, probably I could work out how to get a Python script to run with it and conscript it and shove it on a Docker file, maybe. But this is perhaps a limitation or a big hurdle for any Geohub, is how to overcome the graphical user interface model based on Windows. And if that can be overcome, then you would really have something special. At the moment, this is too orientated towards the person that is already relatively high-end skilled with scripting.
Okay,
And it's not really a question for Georg. This is more something larger. And I don't know if anyone else has ideas of how that can be overcome.
At least I have something to comment here. I've presented basically the same concept last year in Nancy at the Ring meeting. And that's basically where the SkewerGoCAD people are coming from. And someone told me there, GoCAD writes out a list of operations that are done as part of the modeling workflow. And there's a command line interface which allows you to pass in exactly this file to reproduce exactly this operations later on. So you can install GoCAD in a Docker image and just supply that file. And it should technically work. I haven't tried that myself yet, but as far as I know, at least this SkewerGoCAD, it should be possible.
Yeah, so from the GenPy side, the plan that we have actually, and that's something that we have already in the roadmap. So GenPy in principle is stateless. So always that you use the same input, you're going to get the same output. So what we can do is if you just create input in any way, and can be just by clicking on the screen, we can always just store that. And the easiest example that you can think is save a CSV and commit. And then at any stage, you are going to end up with a Git graph, and you can just go back in time. at each step and reproduce how you have been constructing that. Again, you have to be super careful that you are always using the same version, for example, of the program, because in the moment that some hyperparameter, someone, probably me, change a 5 for a 3, your graph is useless if it was not committed. So it has a lot of caveats, but it's doable.
If I may, just to provide some additional feedback about the visualization part, the project which I'm involved in is actually devoted to the system which uses Dockers as well. And a data scientist is supposed to put a Jupyter notebook there. And this notebook should have a visualization part. So once it have a visualization part, the system actually crop it and put it in a separate, separate object, separate window. So the end user actually doesn't see any code, but he see the interactive visualizations. And that's possibly what was John talking about, if I understood correctly. So once we would be able to implement any part of computational tasks within Jupyter notebooks, we can use such systems as Geohub or any other to actually create a number of interactive visualizations which will be suitable for end users to work with without any code knowledge.
Cool. Is that system is that a proprietary thing then, or is that something public? Is that an open source thing? The system that you're talking about, does it?
Oh, that was actually a project within my company for one of universities. I'm afraid I wouldn't be able to show some demo or something. Yeah, but it works, believe me.
Yeah, no worries. It's just I was wondering if it was a system that was also sort of out there and other people might have used it or be able to poke it.
Not yet, at least, but we should think about it.
Yeah. Yeah, so I guess that was the thing that was really missing for me up until this discussion when somebody mentioned GoCAD, and then is now I see that, yeah, the Geohub is a system for running the experiment, but actually it's completely decoupled from where you create your models or where you create your conceptual model, your entire sort of model definition. And you basically plug in any tool then to then just run and execute the workflow.
Yeah.
One of the things I loved about GenPy and PyNoddy as well, did this before it, was you could define a basic model shape and then you could randomize. So you could specify distributions over all the parameters and then generate many models and do sort of something stochastic in terms of whatever your next process was. And I guess in this system, that would all sort of be hidden within the one job. It wouldn't be something that would be exposed on the surface, would it?
Randomizing stuff would definitely be a problem with reproducibility there. So, but it's on the other hand, randomizing stuff or parameters is something I think it's important, but then you should not try to build the one real model, but more like a model distribution where you say, okay, I just put out more than one model and say one of this is approximately reality. So yeah.
But some of the reproducibility issues are still the same, maybe, no? That you still want to make sure that everything was the same except for your choice of seed, maybe.
Yeah.
Yes, but that is a bit where the efficiency is storing files comes into play. So if somehow you are able just to change in memory or make copies in the memory of, again, just to keep it simple, a CSV that has the values that you want to make a stochastic, and you just make many copies of only that CSV, but you don't have to make copies of all the stuff that stays constant, then you can just branch in that way, I imagine. I don't know if branching is something that you are planning, George?
Not really, at least now. Yeah. I keep track of different versions of the construction graph, but I have no concrete plans to implement something like diverging versions or branching there.
Yeah.
Maybe later.
You have the graph. That is the most tricky thing to keep all these things consistent.
Probably I should add the graph can change over time, and you can go back and forward and see how the construction graph looked at a certain point in time. So maybe later you see I have another data set and add another operation to indicate that, for example.
Yep.
Cool. So was there anything else? Anybody else want to say anything, contribute anything, ask a question? Or George, did you have any more questions as well?
From my side, for now, not. I see quite a lot of questions in the Google Doc. I will try to answer them later, and maybe also look in the Slack channel.
Great. I think that's maybe a good idea. Is we can take this document over and continue any questions and stuff in Slack. Great. So if everybody's okay with that, we call it a day on the live session. Yeah. And pick things up in Slack. Thanks all for joining. I hope everybody got something out of it, and we're learning for the next one in terms of format and stuff as well. So any suggestions on format, how I don't know, any suggestions at all on format, give us a shout and we'll incorporate into the next one. Okay,
yeah.
And thanks Georg,
Steve,
for the presentation and taking us through it.
Bye.
Great. Bye-bye.
Thanks, George, too. See ya.